Hello guys, welcome to Physics Grad. This is the second video on the connection between symmetry and conservation, and in this video we are going to understand this by making use of two particular examples. So let us begin. So in our previous lecture we have already seen that the change in the Hamiltonian is given by negative of epsilon times the total time derivative of the generating function g. And if this generating function is conserved, or in other words dg by dt equal to 0, and it is not explicitly dependent on time, then we can say that h is invariant under the transformation generated by g, which in turn implies that the system is symmetric under this transformation. Okay, so therefore whenever there is some kind of a symmetry in the system, it implies or it must lead to some quantity that is conserved as a consequence. Okay, and here in this video we are going to consider some examples of the same. So as our first example, we will consider a case. Okay, so consider a cyclic coordinate qi. Now what do we mean by cyclic? A coordinate that is cyclic implies that the Hamiltonian or the Lagrangian is not explicitly dependent on this particular coordinate. Okay, this is the meaning when we say that the coordinate is cyclic. This also we have seen in one of our previous lectures. Okay, and we know that from our Hamilton's equations we have that pi dot is equal to minus dou h by dou qi, and if qi is cyclic, it implies this quantity is 0, which implies pi dot is 0. So this implies that pi is conserved. Okay, now this is one way in which we have looked at conservation of conjugate momentum when the Hamiltonian is invariant with respect to change in a particular coordinate. Okay, this can also be viewed in another way, that is in terms of transformation under which the system becomes symmetric. So what is that transformation? So that transformation should involve just a change in the coordinate qi alone and keep all the other coordinates fixed. Okay, if that is the case, the system will be invariant, since the Hamiltonian function is not going to change as it is a cyclic coordinate. Okay, so let me write this down. So we can also get the same result using our connection between the symmetry and conservation as follows. Okay, so qi being cyclic is same as saying that h is invariant under a transformation, that h is invariant under a transformation of the form wherein qi transforms to qi plus del qi and the rest of the q's and j's remain as it is. Okay, so this corresponds to identity transformation and only qi changes by an infinitesimal amount. Okay, so we'll call this infinitesimal transformation as equation 1. Okay, so the question is, how do we generate this transformation? Okay, so before that we see that what this implies is that since qi is cyclic, the system is invariant or symmetric under translation in qi. Okay, So when we say the system is invariant or the Hamiltonian doesn't change, it is the same as saying that the mechanical behavior of the system does not change. So it means that the system must be symmetric under this transformation. And what is this transformation? This is nothing but a translation along the coordinate qi. Okay. So we see that if we choose our g of pq to be equal to just pi, okay, then the corresponding transformation from eta to eta plus del eta corresponds to the following. So we know that del eta is given by epsilon j hat dou g by dou eta. So here of course this is the vector notation which we have come across before. So just to remind you, here eta is nothing but the vector consisting of the coordinates q1 to qs and p1 to ps. Okay, transpose, it's a column vector. And J is a square matrix of dimension 2s times 2s having blocks 0, identity, minus identity, 0. Okay, 2s cross 2s, and s is the number of degrees of freedom. Alright. So having said this, if we choose G to be of this form, then what we get is that del Qj is equal to epsilon del Ij, where this is the Kronecker delta function, and del Pj is equal to 0 for all j. Okay. Now this is same as the equation 1. Same as 1, because when I is equal to j, then we get qi going from qi plus del qi, or in other words del qi is equal to epsilon times 1, or this is equal to epsilon. Okay, and epsilon is again an infinitesimal quantity. So this is basically an infinitesimal translation along qi, and for j not equal to I, it is going to be 0, which corresponds to this part of the transformation. Okay, so basically the transformation that is generated by this function is the same as the transformation defined in equation 1. So therefore this is the generating function for the above transformation. Now therefore the connection between symmetry and conservation says that the generating function g, which is equal to pi, must be conserved, because the system is symmetric under the transformation, implies the generating function must be conserved, which is the same result which we got by using our Hamilton's equation and the fact that qi is cyclic. Okay, so here also we got pi is conserved, and another way of looking at it is that the function, when we take pi as the generating function, it generates a translation along the corresponding conjugate coordinate. Okay, and if the system is symmetric about such a transformation or translation along that coordinate, then the conjugate momentum is conserved. Okay, so the same thing or the same result is seen when we look at it from the connection between symmetry and conservation approach. Okay, so therefore if let's say qi is equal to the x coordinate, this implies that the x component of the momentum is conserved. Okay, so this implies if there is translational symmetry along x-axis. Now remember, this should be a continuous translational symmetry, because any finite symmetry can be broken down into such infinitesimal any finite translation can be broken down into such infinitesimal series of transformation. So therefore if there is continuous transformational symmetry or translational symmetry, sorry, along x-axis, okay, then the x component of linear momentum is conserved. Okay, so another way of stating is that if Px is conserved, the system is invariant under a translation along the x-axis. Okay, so this is one example which I wanted to show you, and it makes it clear how the connection between symmetry and conservation is useful when the system is symmetric. Okay, so let us consider another such example, and in this case, instead of translation, we are going to consider rotation of the system about an axis. And what we will see is that when the system is symmetric under such a rotation, we see that the angular momentum component of about that axis of rotation is going to be conserved. Okay, so let us see this. So example 2. Consider a rotation of the system by an angle d theta, that is an infinitesimal quantity, about an axis. Okay, so first, just to simplify the maths and to understand it more clearly, we are going to consider Cartesian system. Okay, and let us rotate the system along z-axis. So what we're doing is basically this. So if this is our z-axis, this is x-axis, and this is y-axis, and let's say that this is a particle of the system. What we are doing is we are rotating about the z-axis. So this is going to go around in this circle. Okay, and we are going from this point x, y, z to another point x dash, y dash, z dash, such that this angle is d theta. Okay, so if I project this circle on the xy plane, then what we are going to get is the corresponding points xy and x dash, y dash, and this angle is going to be d theta. Okay, so now since we only need to observe this part, let me draw it here. Y x, we have xy and x dash, y dash. So if I consider this to be the position vector, then the position vector is rotated by an angle d theta. And we know that such a rotation operation can be represented in the matrix form as follows. So the new set of coordinates x dash, y dash is equal to cos of the angle rotated, which is d theta, minus sine d theta, sine d theta, cos d theta, times the initial position vector xy. Okay, so this is going to be approximately 1 minus d theta 1 when d theta is infinitesimally small. Okay, so this implies that x dash is approximately x minus y d theta, and y dash is approximately x d theta plus y. Okay, so this can be seen as x plus del x, and this can be seen as y plus del y. So from this, what we get is that del x equal to minus y d theta and del y is equal to x d theta. Okay, and of course the z coordinate doesn't change because it is the same along this point. So z dash is equal to z, which implies del z is equal to 0. Okay, so this is our required transformation relations. So let me call this equation number 2. Okay, so in a similar fashion, similarly, since we are working in phase space, we need to also consider what happens to the conjugate momentum. So momentum also can be expressed as a vector in the xyz plane as just p as p here like this. Okay, so when we rotate this vector along the z-axis, now of course the z component of p is not going to change, but the x and y component are going to change. Okay, and the way it changes is same as how the position vector changes. You can verify it, and what we get is that del px is equal to minus py d theta, and del py is equal to px d theta, and del pz is equal to 0. Okay, so let us call this relation along with this relation as equation number 2. Okay, so therefore equation 2 is a transformation that rotates the system with respect to z-axis by an angle d theta counterclockwise direction, in counterclockwise direction. Okay, now once again we know that del eta is given by epsilon times j hat dou g by dou eta, and here if we choose epsilon is equal to d theta, what we see is that del xi is equal to d theta times dou g by dou px, and this implies, if you compare this relation to this relation, what do we see? Okay, so if you compare this relation with this relation, so comparing this relation with this relation, del x, so I don't need an I here, so del x is equal to minus y times d theta. So there is d theta, which implies that this quantity should be equal to minus y. Okay, and if that is equal to minus y, similarly we will get that if you choose for example similarly if you choose del y, this should be equal to d theta times dou g by dou py, and if you compare it with this relation, this guy should be equal to x. Okay, so from this we can make out, if you similarly calculate for del px and del py, what you will see is that our g is going to be simply equal to xpy minus ypx. Okay, so you can just verify by differentiating this equation with respect to x, y, px, py, and you will see that you will get the same relations in as equation number 2. Okay, so therefore this acts as the generating function for this transformation, for this kind of a transformation. Now if you see this is nothing but, if you consider in the xy plane, so if you consider the xy plane, if this is our position vector, and let us say that this is the projection of the momentum operator in the xy plane, what we can do is we can write r as xi cap plus yj cap and pxy as pxi cap plus pyj cap. And if I calculate r cross pxy, so let me call this also as xy because it's the projection of the position vector along the xy plane. So rxy cross pxy, if I calculate this quantity, this is equal to xi cap plus yj cap cross pxi cap plus pyj cap. So taking the cross product, we see that this is equal to xpx k cap, xpy k cap minus ypy k cap, or this is nothing but xpy minus ypk times k cap. Okay, but this is nothing but this is equal to Lz, that is the angular momentum component along the z-axis, because this is the definition of Lz. So r cross p is nothing but the angular momentum, and when you project the position vector and the momentum along the xy plane, it is same as projecting the total angular momentum along the z-axis. Okay, so you can convince yourself about this fact from elementary mechanics knowledge. So what we see is that when we take the generating function to be equal to the magnitude or the component of the angular momentum along the axis of rotation, then the transformation generated by such a generating function is nothing but the transformation corresponding to the rotation about that axis by the infinitesimal angle d theta. And what our connection between symmetry and conservation is saying is that if the system is invariant under this rotation, this implies that Lz must be conserved. Or in other words, if there is conservation of angular momentum component along a particular axis, it implies that the corresponding system is going to have symmetry with respect to rotation about that particular axis. Okay, so if we can in fact generalize this result. So in general, if we rotate the system about an axis along the unit vector n hat, and we find that system is symmetric under this rotation, then we can straight away say that L dot n hat is conserved. That is, the component of angular momentum along the axis of rotation is conserved. Okay, so that is our second example, and nothing special here. You can always choose a particular, so if this is our x, y, z plane and we rotate the system about this axis, say, then this becomes our n hat. We can always rotate our coordinate axis in such a way that z is going to coincide with n hat, and we can perform the same calculation. So this is just the generalized result, nothing special. So in general, if the system is symmetric about a rotation about an axis, then the component of angular momentum along the axis is going to be conserved. Okay, this is what our connection between symmetry and conservation tells us. So these two examples must by now made you understand the importance of this connection between symmetry and conservation, and we will be seeing this again and again as we move along into more interesting topics. So thank you for watching. See you next time.